Yes, it should. It will be kind of confusing if you have upwards, downwards. So make sure that upward is positive, downward is negative. Okay. Let's do stratified flow. For the stratified flow, anyone have a chance to know what page number that we have this kind of picture? Which page number that we have this kind of picture? Any of these? Which page number? Siri? In that book, yes. Which page number? Which one? 64? Okay. Everyone else find that 64? Okay. When you have the book, that is the first step. Okay. Next step is read it. That is the next step. Okay. Next important step. Look at this one. We have definition of angle. This is what I want you to pay attention. Angle is a measurement from horizontal. If theta equals 0, this means horizontal flow. Okay? And we have Vg and Vl. Vg is the actual velocity. Vl is the actual velocity of liquid. Vg is the actual velocity of the gas phase. Okay? Delta L is the length, part of the pipe. Okay? Small length in the pipe length. L is the length in the flow direction. And we don't have any counter current flow of the input. But actual velocity may be backward flow. Okay. Let's say we have other flow pattern. We may, or if we have a stratified flow, can we have a zero velocity of liquid? Sometimes, maybe, if we, depending on what kind of angle. So it may, whatever we put in the bottom may stay at the bottom, it doesn't climb up or something. And whatever stay as stratified on the top, stay on the top. Possible, okay? So, okay, let's take a look at the definition. SG is this length, okay, along the curve. Good. AG, cross-section area. SI, the length of the interface in the cross-section view. SL, this length on bottom. HL, liquid height. D is the diameter. Where else? Gear chain. What is small d? Inner diameter or outer diameter? What do you think? Inner diameter, okay, correct. And we have small p, pressure at this side of the control volume, P plus delta P on the right side of the control volume of the gas. Gravity is downward. And this is the control volume for liquid. Okay. HL is the liquid height, D minus HL is the kind of gas height. Let me ask you, your version. Small HL, this term, small h sub L, and whole up, capital HL, are they the same? Yes or no? No. Are there a lot of different? How close they are? Small h divided by capital D. H sub L divided by small d. Okay, I'm sorry. So this is the ratio of the liquid height per pipe diameter. This is almost HL, but they are not the same. They are not the same. But if your liquid height it is at the half, so liquid height per diameter is 0.5. Also the same as HL, which is 0.5. If the pipe is full of liquid, HLOD is 1. And capital H sub L is also 1. If it's 0, they are both 0. But somewhere else, they are not the same. They are close, but not the same. Okay? Okay, let's take a look at tau WG. Akim, what do you think is tau WG? Yes, correct. It is the shear stress. What is the unit of shear stress, Akim?
Stress is pressure.
Correct. Pascal, right?
Yeah.
Okay. So tau WG is wall shear stress between gas and the top wall. Okay. Shear stress moves against the flow of gas, so it moves backward. Okay. Tau I is the shear stress between gas and liquid. This picture is drawn based on the assumption that liquid moves faster than gas. Oh no, gas moves faster than liquid. When gas moves faster than liquid, this means liquid kind of drag gas back, right? So shear stress at the interface make gas kind of move slower or have to spend some energy to move forward. So that is why when we look at gas phase, shear stress acting on the gas phase is move backward. So if you notice, this is kind of force balance acted on that control volume, right? The interface shear acted on the gas is dragging it back, right? The top shear between gas and wall is also dragging back. Pressure on the left side push it forward. Pressure on the right side push it backward. So this is force balance, free body diagram. Let's take a look at the bottom one. The only thing that you want to pay attention is tau I. You see this time, tau I has a different direction. The size of the arrow is the same. The magnitude is the same, but it is the opposite sign, or opposite direction. Because shear from gas to liquid drag liquid forward. Okay, that is why tau I is in the positive direction. What is it? Raymond, make sense to you? Good? Yeah. Okay. Alright, tau WL drag it backward. And of course, gravity make it go down, straight down, right? So if we have this is theta, then this is also kind of theta, right? What is the direction of rho g sine theta? Arya Shadi. What is the direction of rho g sine theta? Positive x, positive y, negative y. Y is this way. X is this way. Rho g sine theta will be what direction? Positive x, positive y, negative y. Or you want to look at the next slide? What? What is the direction of rho g sine theta?
Negative x.
Yeah, good, right? Negative x. Kind of correct. So let's take a look at the force balance. So if this is theta, this direction is rho g sine theta, right? So when I have force balance, the net force from pressure will be P minus this whole term, right? Divided by cross-section area, correct? So, okay, I put here that if it is in the flow direction, it is positive, okay? Tau and P are force per unit area, and tau I, Si delta L is the force in plus L direction. Akin, what is SL or Si delta L? What is Si delta L? What kind of surface? Si delta L. Oh, really? Let's go back. What is Si?
Oh, okay, I see.
That is the length, right? Si.
Yeah.
And delta L is that. Are they the same? Si and delta L? Yes?
I don't think so.
No, okay, they're not the same. So Si multiplied by delta L will be this kind of interface area, right? That kind of interface area. So if you look at the pipe, and the pipe is kind of long, very long, so that is Si delta L, and this is the direction of delta L. Good, I think. So Si delta L is the area that is acted by tau I, right? Tau I multiplied by Si delta L will be force from the interface, right? That is force from the interface. Si is a straight line. Okay, we assume that Si is straight. So we have interface force. And SL delta L will be this length, this curve length multiplied by this delta L. So it's the surface at the bottom. Okay, it is the surface at the bottom. That is for tau WL, right? So tau WL is the force per unit area, and that area is that curved area at the bottom. We multiply together, we get the force, okay? Tau WL. So tau WL multiplied by area will give us the force in the negative direction. Good? Anders? Good?
Yeah.
Okay. Now we have to find another force. Force in the positive direction is positive. Force in the negative direction is negative. So P delta PAL, this term is positive, right? Plus. P plus dP multiplied by AL. This term is minus because it's on the negative direction. Add them together, we get the net force in the plus L direction. Correct? We get the net force. So net force is minus dP multiplied by AL. That is net force due to pressure. Next we have rho AL delta L. So that is liquid mass inside the control volume. Good. So there is a body force caused by gravity, and that is in the negative L direction. Rho G sin theta is this way. It should be straight, okay? This way. That is rho G sin theta. Then we have mass multiplied by acceleration in the negative L. That is gravitational force in minus L direction, or rho AL delta L G sin theta. So put all force together, you will see that every term has delta L, and delta L, except the pressure term. Right? Put everything together, divided by delta L, we get this equation. Good. So first term comes from this part. minus dPAL, just divided by delta L, and take the limit of delta L go to 0. Second term is tau WLSL, right? Which is this one, divided by delta L. It is in the negative, minus L, so we put minus sign here. Tau I is positive direction, so it's positive tau ISI. Alright? And this is pressure drop equation. Good? You like this? What do we miss?
Consider the gas.
This is a force balance for liquid phase. Just liquid part first. What do we miss in the liquid part? What? Okay, I haven't asked any of these three people. V10, what do we miss? Nothing? We get everything? Is this the same as in your book? Yes or no? You don't know. Nan Chan Lee, is this the same as in the book?
Yeah.
What do we miss? We miss nothing, right? Really? Okay, we may not miss anything. George, what is the assumption do we have? The assumption. This equation valid for what case? Pardon me? Yes, it is for liquid part. What else? Stratified flow. Okay, what else? What? Steady state. Yes, that is one of the assumptions. This is only for steady state. Anything else?
Gas moves faster than liquid.
Gas move faster than liquid. Yes. Okay, this is one of the conditions that we have this time. This is what else for the assumption that we use in here? Friction factor.
The problem is the line something. So we are missing the
What is about friction factor?
we are not considering pressure drops due to friction factor.
We are not considering pressure drop due to friction factor. Is that one of the assumptions?
Neglecting the bit of zero.
Danny, what is the assumption that you think we have here? Friction factor? We neglect the friction factor? Which friction factor that we neglect? If we neglect any friction factor? Seems to be too difficult question. Let's go back to last lecture. Okay. You remember this lecture? What kind of assumption that we can have? Do we have gravitational term in there? Friction term? What about accelerational term? Do we have it? No? Why we don't have? Why can we neglect it? What kind of assumption do we use? And how do we have accelerational term? dPdz subscript A.
First, it has to be gas. Then it has
Really? Does it have to be gas?
Then it has to be lower pressure.
Does it have? Oh, that is true. Generally, in the low pressure below 100 psig, we can have, if it is gas, yes. Look at rho v dVdz. Whenever dVdz happen, we will have acceleration or pressure loss, right? How can we have dVdz? If there is a change in the pipe diameter, velocity could change, right? If we have a constant volumetric flow rate, if there is a change in the density, it expands a little bit, velocity can change. If there's a phase change, the velocity can change. And you will want to ask yourself, whenever you find flow-related equation like, is this for laminar turbulent? Is this for steady state? Or transient? Is it fully developed or developing flow? Should it be far away from the inlet, or it doesn't matter, or it actually matter? Okay, if we want to ask all this question, let's go back. So we have this equation. Now let's see how do we calculate. This is a Taitel and Dukler model. It is a stratified equilibrium model. First, we assume that everything is stratified flow. It is stratified flow, and then we do a calculation. After we do the calculation, if we see that stratified flow is not stable, then we calculate the flow transition. Okay. Similarly, for gas phase, we have that equation. The difference this time is the sign for tau I. This time it is minus. Previously it is plus. Okay, and the reason it is minus is when we do it for gas, tau I drag it back. Okay, tau I drag it back. What if I try to use this equation for the case where liquid moves faster? Can I still use this equation? I can? Really? Vanguard? How do I do that?
Just change the signs.
Just change the sign. Yes, it's not that difficult, right? So if we have liquid flow faster, gas flows slower, we may have to do something with this tau term. We may say, okay, tau I, the value become negative if liquid flow faster, something like that. Okay, I will tell you exactly what we should do later. I have this one, dpdl sub L equal to dpdl sub G. Who else I haven't asked anything? Who want to volunteer? I have a question. Jia Chen, eventually you will finish your doctoral degree and become Dr. Shen, right? Jia Chen, what do you suggest? Why do we have dpdl in gas equal to dpdl in liquid for stratified flow? Why do you expect that?
Because the pressure is the same at all the directions.
At the same cross-section area, do you expect pressure to be the same? Basically, this pressure and this pressure, are they the same?
Yes.
And this pressure and this pressure, are they the same?
Yes.
What if they are not the same? What do you expect?
Lower pressure.
Let's say the top one is lower. So this is lower, that is lower, this is higher, this is higher. What do you expect? There's a difference in pressure.
It wouldn't be stratified flow then?
Yeah, it won't be stratified flow. It will have up-down motion or something, right? It have a driving force to move in y direction. Okay? So it makes sense for stratified flow that it cancels. Okay, let me ask you this. When you see this kind of equation, see this one at the bottom, is this for laminar? Can we use laminar flow for this? Cheng, Jia Cheng.
Yes.
Can you use it for turbulent? That's a yes and no, that's two answers, right? 50% chance. Can you use it for turbulent?
I think it's yes.
Yes. And can I use it for turbulent?
Yes.
Vanguard,
No.
Siri,
Yes.
June? No? Danny?
Yes.
Yes? Okay. June, do you think Shoham used it for turbulence or not? Obadiah Shoham. Did he? Who is Obadiah Shoham? Okay, the other group. Okay. Did he ever use it for turbulent flow? For that equation. Can you take a look on page 64? Page 65. Is there anything about Laplace type equation and have 0.046 times Reynolds number to the power of minus 0.2?
This is a smooth file.
Yeah, that's smooth pi, but it's turbulent flow. Yes. So Taitel and Dukler did that, right? Okay. So this means force balance is for both laminar and turbulent. This part I really want you to understand it, okay? I don't want you to say, okay, we have Taitel and Dukler, and one asks, hey, but this is turbulent flow, how can we use this? Don't say that, okay? It works for turbulent flow. So, if I have turbulent flow, shear chain, is that pressure and that pressure, are they going to be the same all the time? Time equal to 0.001, pressure on the top and pressure on the bottom, are they the same? Time equal to 0.002 second, are they the same? Are they the same every time?
Yes.
Really? Do you have fluctuation in pressure measurement for turbulent flow?
Yes, sometimes.
All the time, okay. Vanguard, what about velocity? V gas at that point, when you measure 1 nanosecond, 10 nanosecond, 100 nanosecond, are they going to be the same? If it is turbulent flow, are they going to be the same? Vanguard, please. Yes or no?
I think not.
Okay. Turbulent flow, there is a fluctuation. That is the point, right? That is turbulent, mixing. You have eddies moving. So, how come this model works? This model, let me tell you, it doesn't have anything to do on the force balance in the y direction. Everything is on the x direction. How can it be valid when there's a fluctuation on the y direction? Siri, what do you think? Why should it work? Do we need force balance on the y direction? Clearly, if it is turbulent flow, at a certain point in time, there is a possibility that there's a velocity in the y direction. Do we need equation in the y direction? No, because Shoham doesn't have it, right?
In reality, it's yes.
Ah. June, what about time average velocity? Let's say we have single phase flow in the pipe. In a pipe, this pipe but just gas. Okay. On average, do we have velocity in the radial direction? Time average. Time average means we measure velocity 1 second, 2 seconds, 3 seconds, 5 seconds, measure several times, add them together, average. On average, do we have velocity on the y direction or we have just x direction? On average, single phase flow. Just x, right? So my point is the time average velocity in some direction is 0. For example, time average velocity for single phase flow, time average velocity in theta direction is 0, time average velocity in radial direction is 0. Okay, instantaneous velocity at y direction may not be 0, and probably not 0, but on average it is 0. When we do force balance like this, it is only for time average. If you go to do the measurement, okay, a grid said density has to be that much, you get it fluctuate up, down. It may not be because of the meter. It may be because the flow itself acts like that. And the equation that we have is for time average parameter is not for value at that point in time. Make sense to you? Okay. A little bit more. So we have equation. All right. What do? We know that dPdL, they are the same. We divided equation 3.26 by AL, equation 3.27 by AG, minus them, subtract them from each other. Top line, subtract by second line, we get the combined momentum equation. Done. Good. So in the combined momentum equation, if you rearrange it, 3.28 in the book. Okay. So in this one, I say it is the implicit equation for HL. If we know the only unknown is HL. If we know VSL, VSG, fluid property, the only unknown is liquid height. Okay. Right now you don't have enough information to do the next homework, but the next time you will. Okay. So there's no more homework for this time. And on Wednesday we meet in what? Lab 201, second floor, the corner. We will stay in the lab not all the time, and after we finish we go back to 204. Okay. Bring safety glass. Did you go to Walmart and buy one? No? Please do so. Alright? This time is enough. The reason that I asked you to bring a book so that I can give away the software, just that. Alright. See you on Wednesday. Bye bye.